Welcome everybody. Today we have as our guest and speaker Professor Artie Hatzes, and so he's in the Thüringer Landessterrenwarte. He's the director of the Thüringer Landessterrenwarte, and is also a professor at the University of Jena. He was born in, I hope I pronounced it well, Havre de Grace in Maryland on May 24th, 1957. That's all on Wikipedia.
And I don't know who put it there.
So it must be correct. And you also studied in California Institute of Technology and the University of Santa Cruz, also in California. And well, as most of you presumably know, Artie Hatzes is famous for discovering numerous exoplanets and being very active in the exoplanet community. And so today we will talk about digging into the dirt, finding exoplanets in the presence of stellar activity.
Okay, thank you. Oh, are there any questions? Can you hear me? Because I didn't put the microphone on, and I usually have a booming voice, so if you put the microphone on, you probably won't hear anymore for the rest of the afternoon. Well, thank you for the invitation to talk about one of my favorite topics, exoplanets. And I'm going to have a little bit of a specialized talk, and it's on digging in the dirt, finding Earth-mass planets in the presence of stellar activity. Now, this figure shows you the evolution of planets discovered by the radial velocity method. You all know this. This is basically, you look at the Doppler shift of spectral absorption lines due to a planet, a star being orbiting around the center of mass due to a planetary companion. You apply Kepler's law and you derive the mass. And here this shows you the evolution of the mass in Jupiter masses as a function of year. And you can see we're going to lower and lower planet masses. And I'll talk about the second half of my talk about a potential Earth mass planet that may have been discovered by the radial velocity method. The reason we're pushing this limit to lower and lower masses is because this shows you the evolution of the radial velocity precision as a function of year. In the 1950s, we were doing 1 kilometer a second velocity precision, and now we're doing under 1 meter per second Doppler shift precision. And if you extrapolate this curve, by 2023, we should have a radial velocity precision of 10 centimeters a second. And what is so notable about this amplitude, that is the reflex motion of a sun-like star with an Earth-mass planet in the habitable zone. This shows you the radial velocity discovered planets. It's not quite up to date, but the current diagram doesn't look much different. And you can see this is the detection limit. And these red dots are the planets in our solar system. These are the interesting planets. These are the planets that are like us. We've yet to discover them. It's not because they're not out there, but because the measurement precision hasn't gotten good enough. We need to push this to better and better precision. Now, if you want to get a better Doppler precision, you need to have a very good wavelength calibration. And a lot of efforts have been taken to improve the wavelength calibration, starting with thorium-argon cathode lamps. Then we started using absorption cells, simultaneous thorium-argon. Now we're thinking of laser combs, Fabry-Perot's, you name it. But the real problem is not the wavelength calibration, it's that the stars just don't cooperate. This is the ultimate thing that's limiting the velocity precision. And here I show you the problem. It shows the various stellar phenomenon, the time scales involved, and the amplitude in meters per second. Stellar oscillation is not a problem because you can, they're rather short-lived. You can average out over many observations. But activity is the big problem. You can have spots on the surface of the star that have time scales of the rotation period of the star, amplitudes up to 100 meters a second, depending on the amount of spots on the surface and the rotational velocity of the star. And even convection, on time scales of up to decades, can produce radial velocity variations of 10 centimeters a second. And so no matter, you can have a super duper stable instrument with great wavelength calibration. The ultimate precision is going to be limited by the star, and you can't control the star. You have to live with it. And one of the main problems is if you have spots on the surface of the star. Here I show you a star with spots. If the star is rotating rapidly, you get Doppler broadened spectral lines. And here, this is an example of a very active star, and these distortions are due to very large spots on the surface of the star that pass through the line cores. When the star is rotating very slowly, you can't see these distortions, but you can measure them with the precise radial velocity measurements, because these are distortions in the line profile that shifts the centroids of the lines. And here I just show you an example. This is some spots I put on a star. This is a spot coverage comparable to what you would get, say, in solar maximum. The star is rotating at 3 kilometers a second, and this is the radial velocity caused by the spots. It's an amplitude of around 10 meters a second. And if you want to find very low mass planets with low amplitude velocities, it's going to be obliterated by the spots. So today I'm going to talk about 2 examples. I think in the abstract I said I was going to talk about LISA 581G. I'm not going to talk about that for lack of time, but suffice it to say that LISA 581G is dead. It doesn't exist. So what I'm going to talk about primarily is on 2 examples of pulling out low mass stars around very active stars. The first is Corot 7b. It's a transiting super-Earth. And then the second half of the talk, I'll present some new results of my analysis on Alpha Centauri BB, which is potentially our nearest neighbor. And in both cases, the radial velocity amplitude due to the planet, to the activity, is 2 to 3 times larger than the amplitude of the star due to the planet. So our tools that I'm going to use for today's talk are 2, the discrete Fourier transform. This is and the procedure of pre-whitening. And for discrete Fourier transform, the amplitude is the velocity that you get is the amplitude of a sine wave in your data as a function of frequency. The Lomb-Scargill periodogram is essentially the same with a different normalization, but in this case, the power is a measure of the statistical significance. Most planet hunters use this. Very few use the DFT. It's mostly done by people who study stellar oscillations. I'm one of the few that actually use both of them. And finally, I'm going to present independent techniques so that you can verify the results you get with the other tools. Now, an important thing that's often not recognized when using Scargill periodograms, the power is a measure of the statistical significance. And the more data, if you have a real signal in your data, the more data you get, the more significant the signal is, and the power goes up. Here I've taken a sinusoidal wave that's noisy, and I take the Scargill periodogram of the first 50 points. You see nothing. Of the next 100 points in the time series, you get stronger power. You add more points, even more power. And as you add more points, the significance goes up and the power increases. This is counter to what you get with the classic DFT. If you have an amplitude in your time series, and it's a constant amplitude and a sine function with a constant amplitude, an amplitude's an amplitude. You get more data, it's not going to change your amplitude. And here I show you the same simulation of the same time stream. As you add more data, you get that the amplitude peaks through, but the amplitude is staying constant as you add more data. So you see the axis here, the amplitude is the same, but what's happening is the noise level is dropping, and the amplitude stays the same. And people who work with DFTs, they can gauge the significance just by looking at the mean level of the noise compared to the amplitude. Scargill makes it easy because the power you see is translated into a significance. Okay. I will be showing you some scarable periodograms today, and as a rule of thumb, you know, I've done thousands of scarable periodograms in my career, and as a rule of thumb, to assess how significant a period is, and if I'm sitting out in the audience in a conference, and you have a scarable periodogram that's less than 6, I'm going to continue reading email. I'm not going to pay much attention. If it's between 6 and 10, I'll look up and say, nah, that's probably not real. I'm going to go back to reading email. If it's between 10 and 14 now, it starts to get interesting. It might be real. It's worth investigating more. And if it's greater than about 20 or 30, I'm stopped reading my email. I'm paying attention because that is a real signal. And like I say, for the DFT, if the amplitude is 4 times the mean, you have a false alarm probability that it's due to noise of about 1%. Okay, another tool I'm going to be using is the pre-whitening. This is the procedure where you basically find the Fourier components in your time series. And it's a very simple procedure. You compute the DFT, you find the highest peak, you fit a sine wave to your data, you subtract that from your data. If you're in the level of the noise, you stop, but if not, you go back to the top and find the second highest peak, fit that, and you can successively fit all the Fourier components in your data. Now, this is a procedure I use in a paper that just got accepted a couple of days ago, where I use pre-whitening, and I'm going to use this pre-whitening to find the Fourier components of the underlying activity signal. And the referee came back and said, I question the validity of using multi-sign components to fit underlying activity signal, which includes trends. And my reply to the referee, well, my, justification is, well, this fellow here, Mr. Fourier, a very clever mathematician, who said a continuous function can be represented by a sum of sine waves because it's a basis function. That's the whole basis of a Fourier transform. So yes, you can use multi-sign components to fit any underlying activity signal, but it's tricky. You have gaps in your data, you've got noise, but there is a mathematical basis for what I'm going to show you. And I remember and here I'm going to show you, you've probably seen this in all your physics classes, of doing a pre-whitening on a linear trend. And no one would argue that there's a sine wave in this data. And I remember when I was, after Caltech, I was working on the Voyager project, and we were going to deconvolve images of Jupiter's ring to deconvolve the motion of the Voyager spacecraft to look at structure, and so we were going to use Fourier deconvolution. And there was an astronomer from Maryland who was visiting us and to help us, and I was, a young, undergraduate, and we go up to, my friend and I go up to him, and this astronomer says, I'm used to thinking in Fourier space. And I thought, this guy's an oddball, but he was right. You have to think in Fourier space, because you in the audience will say, there is no coherent sinusoidal signal in this y equal t function. If you think in Fourier space, you'll say, not only is there one, there's many of them, because when you find the individual Fourier components, you can fit it with a nice, this is what Fourier analysis does. So I'm going to use pre-whitening to find the Fourier components of the underlying activity. Oops. So, test case 1, Corot 7b. This is a very famous planet. It's the first transiting rocky planet. This is the transit curve derived from the Corot Space Telescope. It's a beautiful transit. This is when the planet goes in front of the star and it causes a decrease in the light level. And from this depth, we can determine if the depth is only 0.035%. You got to go to space to measure that. And the radius is 1.6 Earth radii. But we want to get the density of the planet, so we need to get the mass. To get the mass, we need Doppler measurements using spectroscopy. And to do that, and the problem is, of course, is it's an active star. Corot 7, this is the complete light curve. And these big bumps and wiggles are due to the spots on the surface of the star. 2% modulation of the spots. The star has a 23-day rotation period, and here you see the radial velocity measurements taken with the Hartz spectrograph, and these large variations are not due to Corot 7b, the planet, it's due to these spots. And you can see the amplitude of these activity variations is up to plus and minus 20 meters per second. Totally dominates the radial velocity curve. Do we have any hope of getting the mass of Corot 7b? Well, I'm going to show you these are the original Hartz measurements, and I'm going to present also a few more Hartz measurements, and they're listed here. These were taken 3 years ago. We had a run about a year ago where we got more measurements, and the first thing you can see is that the activity level of the star seems to have dropped down. I'll come back to that point later. There's some additional Keck measurements that are contemporaneous to these, and these are summarizes all the measurements, and I've highlighted these are the important points because I'm going to present an independent method for getting the mass of this planet. We have many nights where we have at least 3 measurements taken during the night, and this is going to become important later. Okay, so for the Hartz 1, let's just do our simple-minded pre-whitening. You do the pre-whitening process. There's a nice program. You can download it on the web. Just do a web search period 04 download. It works on Mac, it works on Windows, and it works on Linux. And you can do this Fourier analysis in pre-whitening. You apply this to the Corot 7b radial velocity from the Hartz 1 run, and you get a lot of frequencies. The 3 I've highlighted are 3 frequencies I think are due to planets, and this one here is the exact period of Corot 7b, and there's its K amplitude. How do I know that these 3 are due to planets and all these other signals, about 8 up to 10 frequencies are due to activity? You look at the periodigram of activity indicators. And some of these indicators are things like the bisectors. That's a measure of the asymmetry of the line, how much distortion is in the line profile. There's the full width at half maximum. That's also a measure of the distortions of the line profile. This is the full width and half maximum of the mean line shape. And the calcium indicator, calcium 2 indicator, which is also a measure of plage and activity on the surface of the star. And here are the radial velocity measurements. These are the high frequency regime, so you can see where Corot 7b, the 0.85 day period, or 1.17 cycles per day. This red, this is the rotation period of the star, which dominates all the periodograms, and you see it's everywhere. This is the first harmonic, P rho over 2, P rho over 3, and you can see basically many of the peaks seen in the radial velocity are seen in all the other activity indicators. So you know that has to be due to activity, but there's 3 peaks that you see in the radial velocity, but is not seen in the activity, and that's a signal of a planet, because a planet does not cause variations in any of the activity indicators. You apply your pre-whitening, and this is the radial velocity curve for Corot 7b after removing all the contribution of all the other frequencies. And this is for Corot 7c, because we found, the second planet, a period of 3.7 days. And for the longest time, I thought was a 3rd planet in the system, but no one believed me at the time. I was sort of like the lone crazy guy shouting in the desert saying, there's 3 planets around Corot 7, but no one believed me. Pre-whitening is nice. It gives you a quick answer, but you really need to test it with some independent method. And a nice independent method is the fact that you have 3 measurements per night for a lot of these nights, and the period of Corot 7 is 0.85 days. And so if you were to take your raw radial velocity measurements and phase them to the orbital period of Corot 7b, you get a mess. Why do you get a mess? And let me explain, the color codes are points that are taken on the same night. So every point that has the same color or 3 successive measurements in a night. And the reason you have this big scatter, because at one night, you know, the points will be high due to spots, maybe other planets in the system, and sometimes the points would be low. You come to the same phase, but you have a different spot configuration. So how do you pull out the signal of Corot 7b? It's easy, because in one night, you have 3 points, and they're sampling a part of the sine wave. The only variation on one night is due to Corot 7b because it's a 0.85 day period. Everything else has much longer periods. So all you have to do is basically shift all your points up and down till you get a nice fit to the rate of velocity. And it's 5 meters a second. This one, you can do it by eye, but you're not going to do it by eye, you do it mathematically. And the way to do this is you use every night as independent measurements that have a different offset. They're sampling part of the sine curve, and you have this. So you fit them, keeping the period fixed, but allowing the K amplitude to change and the 0 point offset. And the trick that we're using here is that in one night, most of the variations are due to the orbital motion of Corot 7b. And all the other phenomenon, spots, rotation period of 23 days, other planets, just add a constant value, which gets removed when you apply the offset. And it works. Oddly enough, it works. These are the 3 data sets. Parts 1 and 2 are separated by 3 years. This is the nice phase curve of the Corot 7b planet. And the first thing you notice is that it has what appears to be high eccentricity. How does this technique compare to our quick and dirty Fourier pre-whitening? This is the Hartz 1 data, the Hartz 2 data. This is the K amplitude using the offset fitting, and here's the amplitude with pre-whitening. It works pretty well, although the pre-whitening gives you a more circular orbit. So 2 independent techniques that work quite well. The eccentricity, if you examine the 3 individual data sets separately, you get consistent K amplitudes and eccentricities. So we're starting to think possibly that Corot 7b is in a highly eccentric orbit. The mass is about 7 Earth masses. The density now is a little under 10 grams per cubic centimeter. It may be like, we think it might be a super Mercury. How many planets does Corot 7 have? This is in the first paper by Kilo et al. They thought there was only 2 planets. Like I said, I was the crazy guy who thought that there was a 3rd planet in the system. And when you do look at the Fourier amplitude spectrum of the Hartz radial velocity measurements, this is from Hartz 1, this is from Hartz 2, this is the location of the 2 planets 7D, 7C, this is the rotation period of the star, and you can see the activity level has dropped to lower values, but that the Hartz, the signals at the planets stays constant. So this is the first indication that the activity level is lower in the star during the second epoch measurements, and that you actually have additional planets in the system. You do your pre-whitening, because you can't use an independent technique. You're forced to using pre-whitening. This is the orbital variations of Corot 7c, and here is Corot 7b. These are measurements taken 3 years apart. And to me, this is confirmation that there is a 3rd planet in the system. And the reason is you have measurements taken 3 years apart. The activity level of the star is completely different. Different set of Fourier components you're removing, but you get the exact same answer. So it's very hard to justify that with as it being due to spots. What about the eccentricity? You have 3 planets. Is Corot 7b stable? The upshot is yes, it's stable. And it could be if the outer 2 planets are mutually inclined, you can pump up the eccentricity of the inner planet. So it's not a crazy system. This is what it looks like. compared to our, of the 3 planets, that the star is drawn to scale. And you can see the big worry is now that the inner planet is coming very, very close to the star, and that it's there could be tidal effects. So the upshot in this Corot 7 planetary system, it's a very active star, but we pulled out 3 planets, got the mass of Corot 7b, and maybe even getting information about the eccentricity of the planet.
How does one estimate the uncertainties of
When the orbit fitting code spits out the uncertainties.
Well, what method is it using?
Don't really know. It was Gauss fit that was written by Barbara MacArthur, and it pulls out the and in period 04 it also calculates the uncertainties by the matrix elements. So let me go to alpha Cen BB, which is a very interesting system. This was, I don't know, everyone heard about alpha Cen BB? Yeah. It's been called the most important discovery in the last 10 years. Let's take a real hard look at this. This is the radial velocity variations published by Dumousse et al. And it's phase bin, so you can see here the scatter of the points. It's a period of 3.24 days, and the mass is 1.13 Earth masses. And the question is alpha Cen BB really there? Here is the orbital motion. It's a binary system, so you have to remove the orbital motion. I use a second order polynomial, as does Dumousse. And what they used is a technique called harmonic analysis. It's a multi-sign fit using only the rotation period of the star, and it's harmonics. He wrote over 2, 3, 4. And the physical basis is if you have 1 spot on the star, you see the rotation period. If you have 2 spots on the star, you see half the rotation period, etc. Another way of looking at it is like using epicycles to fit eccentric orbits. If you have a circular orbit, you can fit it with 2 circles by adding an epicycle with half the period. I'm not a big fan of the harmonic analysis method because compared to HARPS 1 and HARPS 2, it gave poorer results. The pre-Whitening gave a much, much better result, and it even failed to detect Corot 7b, which was found by the pre-Whitening. This is the fit to the Dumousse et al. Data. They have 459 points. These are the fit to their data using their harmonic analysis. When they take out the residuals, you do get a peak in the periodogram. False alarm probability is only 0.02%. Let's examine it with 2 methods, our pre-Whitening and our local trend fitting. And for the local trend fitting, here I show you, forget for this for now. Here I have a trend where I've added a planet signal, and I'm going to remove this trend with 2 ways. One using Fourier analysis and pre-Whitening, and the other, which is the intelligent way, is you just fit a straight line, subtract the 2, and look at the residuals. I have a periodic signal in the data. When you do it, they both get consistent results. You pull out the period of this fake planet with the right amplitude. So, 2 methods. Let's look at it, examine the Fourier, the radial velocity of alpha Cen B. This is the amplitude spectrum of alpha Cen B. Here you see this peak, that's the rotation period of the star. 1.5 meters per second. Where's the planet signal? Well, it's right there. You know, if you have a little trouble seeing it, I've expanded it up a bit. And so you're trying to pull out a signal of a planet, and I think I like to give movie quotes. And whenever I look at this Fourier amplitude, I think of 2 appropriate movie quotes. One from Amy, from Wednesday Addams of the Addams Family. Be afraid, be very afraid, or maybe be skeptical, very skeptical about pulling out signals. Or from my fellow Texan who said the deputy was looking at this and saying, well, it's a mess, ain't it, Sheriff? And the sheriff says, if it ain't, it will do till the mess gets here. It is a mess. This is the example of doing the pre-whitening, just to show you, you find your peak, remove it, and you successively find peaks until you get to this peak here, which is the peak of corrosive alpha sin BD. These are the frequencies found by pre-whitening. The first 8 I will call the activity signal, and the 9th frequency is indeed alpha sin B. This is the pre-whitened result. There's the peak. It's false alarm probability looking at the Scargill periodogram is 0.004. It's consistent with Dumus et al. When you fit it. So, can you all go home now? No, not yet. Unfortunately, that time is running out, but I'm not convinced. Because if you take out the signal of alpha sin BB from this Fourier component, add it back in, you should get the same answer. But you get a better answer. You actually get a lower false alarm probability. What's wrong? I mean, something's going wrong. This is the fit to the underlying activity. You can see that it's not particularly good. Why don't we do a better way of doing it? Divide these up into epochs and do a pre-whitening on the separate epochs. You do that, and you get a much better fit to the activity, except for one thing, the false alarm probability is going up. It's getting less significant. So I'm thinking, oh, okay. So let's try a much clever technique, which I call local trend filtering. Don't do pre-whitening. Let's exploit the fact that we do two time scales, a 38-day period of rotation, a 3.2-day period of the planet. You divide the time series into gaps of this period range, and then you just simply apply a straight local filtering of, if you have here, you just fit it with a straight line. This shows you the velocity variations of the planet. If you have a parabolic trend here, you fit it with a second order polynomial. You do the same and you get an exquisite fit to the underlying activity, doing what every planet hunter does. When they see a trend, they just fit it with a trend. And what do you get? The false alarm probability of the planet goes to 0.4. The planet is no longer there. You put in a fake planet, you get out the correct answer. I try other simulations of putting planets with different periods, adding them to the data. You're always getting the planet period out that you put in, but not in the case of alpha sin B. And here, this is just 2 chunks that I've used in the time window. And it's clear that the answer you get depends on how you filter out the activity. Here I have an example of, this is a short time segment of the alpha sin B data. You can fit it with a function here. If you remove these points, you can fit this function. If you delete the top ones, fit this function, delete these points, and fit this function, fit it this way, delete it, fit it that way. All you have to do is delete 21 points, provide different fits, take these residuals, add them into the residuals of all your other fits to the local trend, and you can get the final false alarm probability to go from 0.003 to 0.5. By just deleting 21 points and doing different fits in 10% of the data, I can change the false alarm probability by a factor of 100. If you have a Scargill periodogram and you add data, as I showed you earlier, the power should go up. This is what it looks like with the local trend fitting. What happens when you use simulated data? You take your activity signal, add a planet, add noise, run it through your local trend filtering. This is what should happen. you know, the power should increase from this signal level to that signal level, random noise, even for down to 1.4 meters a second, the real data doesn't behave in the way that it should. And here, just to finish, I'm getting close to the end. Have patience. This is a simulated data set to show you how you can be fooled by noise. This is the Scarble periodograms of residuals after removing the activity signal of a simulated data set. I have the activity signal. I've added a signal to the data. I applied pre-whitening. You get a nice peak at 3.24 days. False alarm probability, is 0.0004. You can phase bin like Dubousque et al. Does, and trust me, binning is sinning. You know, if you have lousy data that you want to make it look better, you just bin it. Would you claim this is a nice signal? Planet signal? Well, publishable. The simulated data was just a multi-sign component fit to the activity without the planet, and all I did was added random noise and then filtered it out. And I got a nice planet signal. So you should be afraid, very afraid. And what you see is going on, this is random noise sampled in the same way as your data. This is random noise added to your activity model, and you see a peak here, and it's very close to this is the real data, so you see a peak near the planet frequency. And so this is a case where you have a noise signal, and if you're not careful, you're going to filter it out. So is there a planet around alpha Cyn BB? This is the technique. This is the sigma fit to the activity, and you can see you can make the false alarm probability change by factors of several hundred. And the presence of this planet depends on how you fit the underlying activity. I think the best technique for fitting this activity is the no planet. And I think with alpha Cyn BB, this planet signal may be noise coupled with sampling and the velocity variations. And just to call up some final quotes from the movies, I think it's appropriate to have a quote from our friend the Terminator, who can say, well, alpha Cyn BB, you have been terminated. This is not exactly fair. You might, with more data, it might come back. So I think a much more appropriate quote is, hasta la vista, BB. Because this means we'll see each other again, and it just may be, with more data, this planet will come back. Or a more appropriate quote, I think, comes from my favorite physicist, Richard Feynman. Science is a way of trying not to fool yourself. The first principle is that you must not fool yourself, and you're the easiest person to fool. And when you're trying to pull out subtle, amplitude periodic signal and noisy data, you can be easily fooled. And here, this just shows you detection limits. What could, I'm just end on a positive note, what could you have pulled out of the alpha Cyn BB data? It's 459 data points, a beautiful data set. This is the K amplitude and the mass of the planet. This is the Scarble periodogram and the resulting FAP as a function of sigma. And this is for simulations, and for the sigma level, the expected sigma level of the ARTS data, you could have easily detected the 1.1 Earth mass planet. If you even get to better precision of about 0.6, 0.7 meters per second, you can even get down to 0.7 Earth mass planets. So to summarize, I think, this second test of alpha Cyn BB, it's an elusive planet. Its detection depends on the subtle ways of how you filter the activity. Fourier analysis confirms what Dubousque et al. Result what they get. Trend filtering does not. It's discrepant. And from test, pre-whitening and local trend fitting should have found the planet at much higher significance than it was detected. A noise peak I showed you can masquerade as a planet, so you have to be very, very careful. And I think alpha Cyn BB is unconfirmed, and I can't prove it, but I think it's a combination of noise, sampling and the filtering process. And pre-whitening is a very useful technique, but check results with other method. If you use pre-whitening and on the referee, you're going to catch hell from me because you need. It's easy to get fooled by pre-whitening. It's a nice technique to give you a quick answer, but check it with other means. And I think we can detect planets with less than 1 Earth mass in short period orbits. What about Exo-Earths? And I'll leave this as the last view graph. This is a nice simulation from my friend Mike Endel, who investigated. They're actually looking. This is actually for Alpha Cent A, I believe. And these are simulations where if you have, these are real measurements taken on this star with a 2 to 3 meters a second, and he's replicated these measurements so it looks like he's gotten 46,000 measurements with this precision. He added a false planet in the signal, and the signal pops out. This is an amplitude of only 15 centimeters a second, and with RV precision of 2 to 3 meters a second, you can find this Earth-like planet. You just need 50,000 measurements. And so it's easy to find Earth mass planets with stars with high level of activity. You just need truckloads of data. You just throw telescope time on it. And that is why I think we need a dedicated telescope for RV measurements. And with that, I think I'll quit before I go too long.
So thank you very much. Very interesting. I realized I made a mistake when I introduced you as being famous for finding planets. Now you're also being famous for destroying them. But
and you know what? It's a lot more satisfying to destroy. There's lots of people finding them. Few of them are destroying them.
Okay.
Yeah.
That's a good point. Yeah. Okay. So questions. And maybe we start with the juniors. Students. Yeah, please go ahead.
I'm not very familiar with the technique. I just like to clarify possibly how the spots put the imprints onto the line features, such that you can mix this up with the radial variation.
Well, the spots produce a distortion in the line profile.
But I thought you just could really define distinguish between the radial variation and
The way you measure a velocity of a spectral line is you measure its centroid.
Yes.
Now, if you have a spot on one side of the star, it distorts the spectral line, and it shifts the centroid. And you measure that as a velocity shift. It's not an overall shift of the line, which is what a planet would do. It's a distortion of the line, which also shifts the centroid.
But you can just looking at the shape of the line.
This is why, when I showed you, you look at the bisectors or the full width and half maximum, and when that happens, if you get the same periodic signal in the bisector as you do with the radial velocity, then you know it's a spot.
Okay.
But the problem is, if you do that with alpha Cent dB, you see, the bisectors aren't changing, it's not due to activity. Well, if it's due to noise, you're not going to get a bisector variation. The signal's not there. You're being fooled.
That's fine.
Yeah.
Are different spectral lines more or less sensitive to the presence of spots? Is it
Yes, and actually, this is, I remember Zvi Matze, he once had a great comment that said, there's 3 types of questions. There's good questions, very good questions, and excellent questions. The good questions, I don't know the answer. The very good questions, I know the answer. And the excellent questions that I have a view graph that is pertinent to the question. And actually, this is a little advertisement for the local institutes, is that in the infrared, if you have spots, the radial velocity signal is going to be different because the contrast is different. And so ideally what you will want to do is measure the radial velocity amplitude in a different wavelength region. And the institutes here are working on a very nice instrument called Harmonic that I hope it makes it to Palo Alto, but it's in its final implementation, it will be an optical and an infrared spectrograph where you take both measurements simultaneously, and if you have activity that you think it's due to a Earth-like planet, like around Alpha Centauri b, well, if you're taking the measurements in the infrared and the amplitude is different, then you know it's activity. So the answer is yes, and there are ways to do it.
Okay, shall we open to everybody now? So, any further questions?
So what about, are there different types of stars and
Maybe
Yeah.
you need to repeat the question.
Are there less types of stars, are there types of stars that have less activity? And the answer is yes, very old ones. Typically, when a star is very young, it has a lot of activity. A star like our sun has a lot of activity when it's very young, and as it gets older, its rotation slows down and it gets less active. So if you want to look at stars that are not very inactive, you just have to find very, very old ones. But that really restricts your sample.
I have a question. When you took these 3 data points per night, and then you shifted them until they kind of get on a nice curve, wouldn't it be then better to look at not the curve itself, but the derivative? Because actually that's what you sort of measure, right? I mean, derivative and second derivative is what you measure each night.
Yeah. I actually did that. You basically get a slightly worse result, but you get the same answer. And in fact, in the original paper where I presented this offset fitting, I had a section on derivative, and then I thought I took it out because it make the paper shorter. But yeah, you can use the derivative as well.
Why would then it be worse result?
Well, because you're taking differences and your error goes,
Okay.
is a little larger.
About just a general question about the long spiral periodogram. What happens when you have an eccentric signal? Don't you get smeared out power across many frequencies? So you say, oh, I don't have a planet, but actually it's just because it's eccentric.
No, you don't get what you get is I told you the answer when I said that the harmonic analysis is a lot like fitting eccentric orbits with circular orbits. If you have an eccentric orbit, you can have a circle, a sine wave or a circle, and then you put another circle with half the period, and you get a nice eccentric orbit. So what that looks like in Fourier space is you see a peak at the orbital frequency and all the harmonics.
Yeah.
One peak here, another peak there, and another peak at.
But then you have to mentally add the power of these peaks. If you want to know whether you should read email or not, you have to check whether I have a 7 plus a 5 plus a 3. That's more than 16. It could be.
Well, no, but the dominant peak is really from the primary period, and even in an eccentric orbit, that shows in a Scarble periodogram.
Up to what?
And if you see the higher harmonics, you know it's an eccentric orbit, and I shouldn't be fitting a sine wave to this, and then you use an orbit fitting code. The Scargle is only good for finding the period. Once you find the period, you fit Keplerian orbits.
Artie, I'm wondering about differential rotation in stars. How well do you actually know the stellar period? Because if you look at the sun, different stars rotate in different speeds, and if the spot is here or there, it would make a difference, right?
Yeah.
Which must be appreciated.
Yeah.
How do you cope with it?
Well, if you have enough data, you will see extra periods due to the differential rotation rate? The answer is not very well. If you have, activity is complicated. And if you have differential rotation, the activity signal can get to be really a mess. So the answer is you can't deal with it very well unless you have lots and lots of data and you can pull out frequencies due to differential rotation.
But if you have lots of data, your time coverage is large and spots come and go and you have again a long period variation.
Yeah, it's you do. And that's why when you try things like pre-whitening and fitting Fourier components, you have to be wary of what you're doing. And that's why doing tricks, cutting up the time series into segments and hope that over this segment the star is very well behaved. It's a difficult problem. I mean, I don't think there's a robust way to deal with it for every star. You have to kind of do it on a case-by-case basis.
Concerning the same point which is Dylan has, when you shift these observations of one eye up and down, this works because the change of the background of the noise is much slower than the peak. So it would only work for...
It only works for very short period planets. This is why I couldn't do this for Alpha Centauri B because the period was too long. Otherwise, I would try the same technique, but wrong period.
What struck me is that there seems to be still a lot of discussion about what is the best method to do something. And I had thought that, by now, after so many years, people would have kind of agreed on kind of, a checklist and methods. That if you do this and this and that, then we officially call it planet.
That's a good question, and I wish they would have this checklist. There's, it used to be, we would call it a planet if it had a formal false alarm probability of 10 to the minus 4. Now planet hunters say, oh, it's 1%, that's good enough. And here I've shown you, with Alpha Centauri B, what does this false alarm probability mean? You can get an artificially low number, and they need this checklist because, otherwise there's, planets are going to be pulled off the list.
Time for a international workshop.
Actually, you're absolutely right. I think the IAU should set down criterion of what you have to fulfill before you can go out claiming that this is a planet. I mean, and with this Alpha Centauri B, I was a little skeptical when I first did the pre-white and said, oh, okay, it's there. And then I thought, okay, let's be a little more clever with the filtering, and it just goes away, and I'm just convinced it's not. More data may not, I may be wrong, maybe they get more data and it pops back out, but I think it was premature to.
What do you think of Blender?
Blender.
What is Blender?
Blender is if you have a transiting planet and you want to verify it. For example, if you have a transit of a hot Neptune and it's around a 14th magnitude star found like say with Corot or Kepler, and there's no way in the world that radial velocity measurements are going to confirm it. And this is especially true if it's an Earth mass planet. No way, there's no telescope that'll do it. So you have to convince yourself, is this really a planet? And this Blender looks, I think, correct me if I'm wrong, in the parameter space, figuring out what are all the possible configurations of a false positive. You have a background eclipsing binary, you have a background M dwarf with a Jupiter that's transiting, that's contaminating your system, and you kind of do a probabilistic, like a false alarm probability to say the chances that this small transit is due to some other phenomenon that's not a planet is X, some small number. And what I think of it, it's a more sophisticated false alarm probability, but it's not the final answer. I think it's useful for maybe prioritizing. If you eventually want to do radial velocity measurements, have a list of priorities. Basically, it's the best you can do. What do you think of it?
Well, I'm a potential customer for it, and I'm quite skeptical, so
This is good. It's good to be skeptical, but user beware.
Well, this of course gives a little bit the problem that the good guys who are skeptical will never get the big Nature article because you always do the extra checks, right? And the bad guys will then get the Nature.
Well, my wife once asked me, does anyone have press release when someone says that something is not a planet? I said, no, when it's announced a planet, you get lots of coverage, and then someone comes along and says, no, it's not a planet, and you did get no coverage. And she says, well, then what's the point? You can just publish fake stuff all the time. That gets the publicity. And I told her, but I have to sleep at night.
Okay. Any further questions, or I think this was a very good final sentence. Unless there are. Is there any? No? Okay, then let's thank Artie again.